All right, so we are going to start on the third set of slides and start talking about stereochemistry. All right, so stereochemistry is studying the 3D shape of molecules, right? If you think about it, molecules make up everything that is in the world, and everything you see in the world has 3 dimensions, right? A height, a width, and a depth. So it only makes sense that their building blocks also have a height, a width, and a depth. So stereochemistry is looking at the 3D orientation of group cell molecules and their 3D shapes, right? Like we've already kind of seen this. If you think about, right, cyclohexane is just not a flat hexagon. It exists in a chair conformation, right? And this bond is in front of this bond, and this carbon is above this carbon, right? So you've already seen where our molecules have 3-dimensional shapes. So stereochemistry is really starting to focus in on learning about their shapes and how that then impacts their properties. So we're going to revisit isomers real quick. Isomers are molecules. Oops. So you remember isomers are molecules with the same formula but different structures. And the easiest of these we've already talked about, and that's constitutional isomers. Right, the atoms are bonded in a different order. Right, so where's my mouse? There you go. Oh. See, now that I forgot to share, I'm like, did I actually start the recording? And I did. So, okay. So the example of this that we've already seen is something like butane versus 2-methylpropane. They're both C4H10, right? But they're clearly different structures. So constitutional isomers are easy, right? They look different, right? Then there's a second type of isomer, and that second type of isomer is called a configurational isomer. No, sorry, it's called a stereoisomer. I got ahead of myself. A stereoisomer. The stereoisomer, right? A molecule or molecules that differ by how the atoms are arranged in space. So the atoms are all hooked together the same, right? They're in the same order. You would name the molecule the exact same way, but just how that atom has oriented its atoms in space changes. So we've already talked about one type of these, and that's configurational isomers. I'm going to do examples in a second. Don't worry. Oops. So configurational isomers can change by rotating a single bond. Right, so think about Newman projections, right? This and then this. If I were to ask you to name the molecule, name the actual molecule, right? These are both butane, right? One is in the anti-staggered conformation. And one is gauche, right? It's the same molecule, but how the atoms in that molecule are arranged relative to each other in space changes. So they're in different, wait a minute. I don't have any videos to use today because they're all garbage. This is conformational. I will now feel shame. I'm going to put myself in the corner. I'll let you fix that. I'll think about what I've done. All right. I even turned the camera so the Zoom people could see that. All right. Sorry, guys. They're conformational isomers, right? And you can get from one conformational isomer to the other just by turning a single bond, right? And when I say single bond, I don't mean one bond. I mean a carbon-carbon single bond, like that, just a carbon that has one bond between another carbon. Right, so you can get from one to the other. Another example of a conformational isomer would be a ring flip, right? This and this, right? They're both methyl cyclohexane, but in one conformation, the methyl group is equatorial. In the other conformation, the methyl group is axial. Right? Same name, but they are arranging their atoms differently in space. Now for configurational isomers. Dear God. You cannot go from one to another, so one isomer to another, unless you break a bond. So if you have one configurational isomer, it's always going to stay that isomer. It's never going to go to the other one. It's always going to be fixed, right? So examples of this are like cis/trans in double bonds, right? Or easy. So this double bond is trans. The two methyl groups here and here, they're on opposite sides of that double bond, right? They're across from each other, across trans, verse this is the cis isomer. The two methyl groups are on the same side, right? They're cis. Double bonds aren't able to rotate, they don't turn. So if you have a bottle of the trans isomer at room temperature, it will always stay the trans isomer. It's not able to go from the cis to the trans because the only way that it can do that is you would have to break a bond. You'd have to break that double bond, and you can't do that under normal conditions. So the configuration of being trans is locked and never changes. Another example of this is in rings. Oops. right? So let's say I have a cyclobutane, right? I have in this on this one, this is cis, right? The methyl and the chlorine are on the same side of the molecule, and this one they are trans. And because we're in a ring, I can't rotate the single bond between them. Like I can't turn this bond right here all the way around, right? If I try to turn that bond all the way around, I have to break the ring. Let me close here, huh? Right, here's my ring. If I try to rotate all the way around, the ring would have to break, right? So I'd have to break one of the bonds to rotate all the way around. So in a ring, if, let's see here, try to rotate, I have to break the bond, right? I can't rotate all the way around. So in a ring, if you have your group start cis or trans, you can't rotate far enough that they ever go to the other conformation. So cyclohexane really illustrates this well with the ring flip. So let's look at that real quick. And I'm going to do this, but like the last like 4 or 5 slides in this slide set are just on this. So this is just to illustrate, but if it looks super confusing, it will make more sense later. So let's say I have a cyclohexane. Those two groups are trans to one another, right? The chlorine is pointing up, the methyl group is pointing down. This is trans. If I do a ring flip, right? So this carbon right here is this carbon here. Orange carbon is orange carbon. When you do a ring flip, everything that's equatorial becomes axial. Everything that's axial becomes equatorial. So I end up with this, and this is still trans, right? The chlorine kind of points up a little bit. That's easier to see, right? But this methyl group, it's kind of hard to see that it's down. But if you think about the hydrogen is also on that carbon, that hydrogen points straight up. If that group's up, the methyl group has to be down. So even though I've turned as far as I can possibly turn in the cyclohexane, which is do a ring flip, my two groups are still trans to one another. They're still on opposite sides of the ring. One is up and one is down. So there's no way that you can turn far enough that you can ever get from the trans isomer to the cis isomer. If you try to turn that far, your molecule breaks before you get to being the other configuration. Reasonable?
So I was asked here why the carbon that is orange in this drawing looks like it moves to another position. I was just trying to explain how to think about how a ring flip works.
Okay, so orange dot. Yeah. So if you think about it, it kind of doesn't move, right? So the red carbon comes down and that orange carbon kind of stays put, and kind of the bond from the orange carbon to the red carbon pivots almost at that orange carbon. And so like you can almost think about it as like the two carbons in the back, right, kind of shift forward, kind of slide forward, but those front two carbons kind of stay in the same place, if that makes sense. So you're just kind of pivoting on that orange carbon. And the last example of configurational isomers are chiral centers. Slash carbons. So I will use like chiral center or chiral carbon kind of interchangeably. Say carbon bonded to 4 different groups. So it's not, it's that the four groups that the carbon is bonded to are unique. There's none that are the same. So something like chlorine, bromine, fluorine, iodide. This carbon is chiral because it is bonded to four different things. So a quick refresher on how this stuff's drawn. This bond and this bond, this is in plane, right? So the bromine and the chlorine, they are drawn and they're in the plane of your page or the plane of your screen. They are flat, right? A wedged bond is up slash out, right? So that fluorine, because it's on a wedge, is pointing out of the page at you or pointing up towards you, however you want to think about it, right? It's popping straight out. The iodide is on a dash. That is down slash in. So it's pointing down into the page, or it's pointing down away from you or into the page, right? So whenever you see a wedge, it's sticking out at you. It's like, yeah. Whenever you see a dash, it's pointing away from you. Also, yeah, but in the other way, right? So when we're looking at molecules like this, you have your in-plane groups and then your groups that are wedge and dash, right? So a chiral carbon is going to be bonded to four different things. If we look at, now, you're looking at, when I say four different things, you're looking at everything that's attached to the carbon, not just the first atom. So let's say I had something like this. This carbon is bonded to four different things. Even though it's bonded to two carbons, you're looking at the whole thing. So you've got a methyl over here versus an ethyl, right? Those two groups are different. So even though there is a carbon bonded to that central carbon, bonded to this carbon right here, you're looking at the fact that it's a methyl versus an ethyl. So those count as two different groups. So we're going to stick on chiral carbons right now, right? So only sp3 carbons can be chiral, right? So chiral carbons can only have single bonds, right? So if you have a carbon that's part of a double bond, that carbon can't be chiral. It can only have single bonds. So we've got chiral centers, also called chiral carbons. They're also sometimes called stereocenters or stereogenic centers. I know. Someone in the early class was like, why do we have four different names for the same thing? I don't know. I want to say this a few times throughout the semester. I don't make the rules. I just live comfortably beneath them, and then I tell you about them, right? They don't invite me to Switzerland to like figure out like the naming conventions and stuff. I just report, right? So we have to have sp3 carbons. They're called chiral centers, stereocenters, stereogenic centers. Right. This is what I'm doing. So a compound with a chiral center has two isomers. All right, so if you have one chiral carbon or one chiral center in your molecule, you know you have two isomers, right? These isomers are called enantiomers. They are non-superimposable mirror images of each other. I can show you enantiomers with your hands. Your hands are enantiomers. They are non-superimposable mirror images, right? If you drew like if you think about if there was a mirror between your two hands, right? This hand reflects perfectly onto this hand, right? So your left hand reflects perfectly onto your right. There's no way that you can superimpose, just slide them over and have everything match, right? You can take your hands like this and you can slide them over and the backs of your hands will line up and the palms will line up, but your fingers don't match, right? Or you can flip your hands like this and get all your fingers to line up, but now your palms aren't facing the same direction, right? One's facing to the left and one's facing to the right. But you can never get them all to everything to line up perfectly with your hands, right? Your hands are enantiomers, right? Molecules that are enantiomers kind of work the same way. You can usually line up two things, but you can't line up all four things because they can't slide on top of each other. So let me show you, right, what I'm talking about. So let's do a molecule here. So let's take carbon. We'll go back to this guy. Right, and we're going to have a plane right here. So a mirror plane. And they're going to reflect our molecule across that mirror, right? So everything that's close to the mirror in the original drawing needs to be close to the mirror when we mirror it over. So it's going to look like this. So, do we agree that those are mirror images of each other? Okay. So, if these are mirror images of each other, I can take the molecule that is on, this is like hard for me, I guess on your right, right? And I can flip it over, right? So I can take it from like this and flip it, and all the carbons will line up, right? So if I flip this over, right? If I take this one and flip it, right? All the carbons will line up. No. My carbons line up, right? We on board with that? Like you can see that sliding right over. But the act of flipping it over, my bromine was pointing this way, right? It was pointing out at you. I flipped the molecule over. Now the bromine points back, right? So when I flip the molecule over, now the chlorine's out and the bromine's back, right? So now the chlorine and the bromine don't line up anymore, right? They don't overlap. So I can get the carbons to all line up, but I can't get the bromine and the chlorine to line up, right? Non-superimposable mirror images, right? If I left them the way they are, the bromine and the chlorine line up, right? The bromine's out, the chlorine's back, but then the carbons don't all line up, right? One methyl group points to the left and one methyl group points to the right. Also, real quick, so the way that we draw these, right? We draw our wedges and our dashes, right? There's kind of like they kind of go like left and right to some degree, right? That bromine, think of it as it's straight forward. The chlorine is straight back. So when I say I could just slide them over and they would line up, they don't line up the way they're drawn, right? But they line up how they physically are. Because even though that bromine is on a wedge and pointing to the left in one of them and on a wedge and pointing to the right on the other one, they're just straight, that bromine is just straight forward. right? They just are like left and right because that's how we draw stuff. That's how we write. That makes sense? So just think of when you see something on a wedge, it's straight forward. It's pointing straight out at you. It doesn't have a left or a right to it. All right. So if you have a chiral center, or I guess if you have an enantiomer, if a molecule has an enantiomer, oops, it is chiral. So here in a few slides, we're going to see that you can have a chiral center, but the molecule overall is not chiral, right? So if you have a molecule that has an enantiomer, that molecule, that whole molecule is considered chiral. Right? Chiral molecules, they have no plane of symmetry. Right? So there's no way that you can draw a plane through your molecule that all the that it's going to have symmetry across that plane. Right? So, for example, we'll go back to my little, right? So fluorine, chlorine, bromine, iodide. There's no way I can try to cut that molecule that everything on either side of a plane that I draw through it will be symmetrical, right? And this is true for any carbon that has 4 different groups on it. No carbon that has 4 different groups has a plane of symmetry. Now, as soon as 2 of those groups match, right? Now you could think about putting a plane of symmetry through this molecule that kind of cuts through that central carbon, the bromine and the iodide, and cuts the molecule in half, and you'll have a methyl group on top and a methyl group on the bottom, right? And so there'll be symmetry about that plane, right? So that plane would kind of be coming like out at you. It's kind of, if you went like this, for you guys it's easier, kind of like that, but through the bromine and the iodide, like the bromine together, yeah, right? So you kind of cut that way, and there's a plane of symmetry that goes through your molecule. Right, so as soon as you have, right, it's kind of like, it kind of is, there's kind of your plane, as best I can draw it, right? It kind of cuts right through there, and you have a methyl group on top and a methyl group on bottom. So what I did in the other class, I'll debase myself here as well. Gotta move this. Whoop. If you get motion sickness from me moving the camera, I'm sorry, but I only have so much stuff I can do here. All right, we're gonna stop sharing for a second. Ugh. Okay, you get big me, and we get to see Emily in a black box. Here we go. Can you see my feet? I might not be able to see my feet. Quick, move stuff. Break the room. Forward, forward, and feet. If you cut me across my hands, I'm not this flexible, right? Then you cut me right in half along my arms, and I'm symmetrical, right? My feet should be the same, I hope, right? If you cut me like perpendicular to that across my legs, like split my legs in half, then I'm symmetrical with my hands matching up, right? That's molecule Wakefield. Back to the safety of the little white box, or the big white box in the little Wakefield. Now I have to hit the share button. Right, so that's what you're doing when we're looking for a plane of symmetry, is you're trying to find which bond or which 2 bonds you can split and have the other two sides be the same, or the other sides be the same. If a molecule has a plane of symmetry, it is achiral. And achiral just means it's not chiral. The big thing that comes out of being achiral means that, again, kind of like circular logic here, you have no enantiomer. So far, so good? Okay. So there are three ways to draw enantiomers or chiral centers. I'm going to start with the way that sucks the least and the way that we're going to use the most. And then I'm going to show you how they do it in biology and biochem. We're all going to feel dirty and then move on. All right, so way one is the perspective. What is this? Perspective formula, right? That's where you basically are building off of a skeletal structure, where you have your skeletal structure and you have usually the longest chain or just a carbon chain is going to be in the plane of the molecule, and then you're going to have wedges, oops, and dashes coming off of a carbon. And so what this is saying is that the carbons, right, the four carbons that make the carbon chain, those are in the plane of the page. The OH is sticking straight out at you. The methoxy group is pointed away from you. And just like I talked about, there's no left and right to the OH and the methoxy. So if I were to draw it like this, these two molecules are exactly the same, right? Because when you're on a wedge, you're not pointing forward and left or forward and right, you're pointing straight ahead. So it doesn't matter that the OH on the one is pointed to the left and the other one's pointed to the right. They're physically pointed straight out. And then the group on the dash is pointed straight back. So there's no left or right to it. So these are the same molecule. Everyone see that? .99% of the time, I'm going to draw perspective structures because I think they're easier. And every organic chemist uses these. So there is what's called the wedge dash. So now we're going to go to the Stone Ages, right? And the first thing from the Stone Age is wedge dash, right? So I'm going to draw something that is, say, we'll use the same thing. So we're going to have a carbon, and the groups that are horizontal are going to be pointing out at us. They're going to be on wedges. And the groups that are vertical are going to be dashes. So if I were to look back at this real quick and fill this in, yeah, so it'll be, and it should be OH and methoxy. So this is the same molecule that we just had, but in wedge dash. So what you're basically doing is the wedge dash version of a molecule is you've basically taken the molecule and you've tipped it back, right? So instead of the methyl and the ethyl being in plane, you've kind of taken it by the oxygen, by the OH, and pushed it. So now the OH and the methoxy are both pointing back. So they're like this. And then the wedge and the dash, the methyl and the ethyl are pointing out away from you. Right? So instead of being like in plane and out, here's my OH, here's my methoxy, I've done that. Be harder for you guys to see, but so here's my OH, my methoxy is behind it. I've tipped it forward, or sorry, I've tipped it back. So now my methyl and my ethyl stick out, and my other two groups stick back. I will bring models on Friday, and I will show it, and it will make more sense. Hopefully, then you'll get to the stereochemistry lab at some point, and that will help as well. Great, so that is wedge dash, is you've just taken the perspective drawing and you've tipped it, right? And then the next thing is the Fisher projection. So Fisher projections are the wedge dash without the wedge in the dash. So Fisher projections, make sure I have this right. OH was up. Yep. So Fisher projections are, you are expected to remember that the groups that are horizontal are up, and that the groups that are vertical, are down. So you no longer have the wedge in the dash drawn for you. The wedge in the dash is gone, and you have to remember, hey, horizontal group is up, vertical groups are back. Now, I told you that 99.99% of the time, I'm going to do perspective drawings. Why am I showing you this for the 0.01%? And that 0.01% is basically this picture right here. And this is because that in biology, in biochem, they love them some Fisher projections. They love them. They can't get enough. You're going to go to biochem, and they're going to draw all their sugars like this. They're going to draw all their amino acids like this. And so when you go, and then Lee goes, why can't they do Fisher projections? I can say, I showed them once. I did my part. I hate these things. So I'm like waiting on like the last few sugar chemists to die so we can stop using these. These come from before we had computers. You know, what? And we had to like do stuff with typewriters. So to draw structures, you could make a typewriter draw a horizontal line, and you could make a typewriter draw a vertical line. So they could use these to show stereochemistry, to show that their molecules were three-dimensional without having to like actually able to draw anything interesting. It is also going to be embarrassing too, because if we're not all dead by next fall, knock on wood, right? Again, if I told you an asteroid was coming, you'd be like, I gotta Google it. It might be true. Like, right? We had murder hornets. What crazier things, right? Right? Is you're gonna be in biochem and you're gonna be like, hey Wakefield, how do I assign R and S to this stupid Fisher projection? And I'm gonna go, this is embarrassing. I don't know. I'm going to have to draw it in a perspective structure. Right? So the big thing with perspective is you have in-plane groups, you have like your wedges and your dashes, right? These are still skeletal structures. So even though I'm not showing the other group, right? You know it's a hydrogen, and you always just end up filling in the group that is missing. So every carbon in a perspective drawing has two groups that are in the plane, a wedge and a dash. Right? So you see here, I've got my two groups in plane here and here. I've got my wedge, and then I don't see a fourth group. You know that fourth bond has to be to a hydrogen. And because you have two in planes and a wedge, you know it has to be a dash to the hydrogen. So you know the hydrogen is back. So even though that hydrogen is not shown, you know it's there and you know it's stereochemistry. Same thing over here. I've got my two in-plane groups. I've got my wedge, or sorry, my dash. The group I don't see is a hydrogen. And that hydrogen has to fill both being the fourth thing that's bonded to the carbon, and I need to have a wedge group. Make sense? Seem reasonable? I might, oh no. He's a rookie. He forgot to like share his screen. Oh man, what a scrub.